Hello, everyone. Welcome. My name is Jennifer Nyman. I'm a senior principal at GeoSyntech Consultants, and I have the pleasure of facilitating today's webinar. The webinar today focuses on DoD-funded research efforts to develop innovative approaches for detecting underwater buried targets. First, Dr. Aubrey España from the Applied Physics Laboratory at the University of Washington will talk about UXO classification architecture to assist in post-mission data analysis and the characterization of a set of inert UXOs at a demonstration site. Second, Dr. Steve Kargl, also from the Applied Physics Laboratory at the University of Washington, will discuss his recent work to package the target in the environment model, a fast acoustic model that can predict stave-level sonar signals under various environmental and geometrical conditions into a tool that can be used by researchers and contractors. Each presentation will be followed by a brief Q&A session, and we will conclude today's webinar with a longer Q&A session with both of our speakers. The next couple slides provide instructions on optimizing your webinar experience. If you haven't done so, you can download Zoom at the link shown here. If you can't download Zoom, you can view the slides using a compatible internet browser like Firefox, IE, or Edge. If your screen freezes, you can try keying Control with F5 to perform a hard refresh. In case of continued difficulties, you can download the PDF of the slide from the webinar webpage and call into the conference line. We will also be live streaming the webinar. Today's broadcast will be listen only. You may submit questions using the Q&A box on your screen. Please submit questions in advance of the Q&A session and add your organizational name at the end of the question. Please don't submit questions in the chat box. And with that, I would like to introduce Dr. Alison Marizano, who is a toxicologist at the Defense Centers for Public Health, Aberdeen. Alison is assigned to SERDP and ESTCP, where she serves as the Deputy Program Manager for Munitions Response. Alison's applied research background is in characterizing health hazards of defense-relevant chemicals, including green and insensitive munitions and PFAS. Alison received her BS in biology from Penn State University and a doctoral degree in toxicology from the University of Maryland, Baltimore. Alison, please go ahead.
Great, thanks, Jennifer. I'm happy to welcome everyone to today's SERDP and ESTCP webinar. In the next few slides, we'll provide a quick overview of SERDP and ESTCP. SERDP and ESTCP are the Department of Defense's investments in environment and installation energy science and technology. The programs report to the Deputy Assistant Secretary of Defense for Energy Resilience and Optimization, headquartered at the Pentagon. SERDP is the Strategic Environmental Research and Development Program, and this was established by Congress as a partnership between the DoD, the Department of Energy, and the EPA. SERDP addresses high-priority environmental science and technology opportunities that focus on the top priority DoD requirements. SERDP funds both fundamental research as well as advanced technology development that ultimately impact real-world environmental management. ESTCP is the Environmental Security Technology Certification Program, and this is where we demonstrate and validate innovative environmental and installation energy technologies. These investments capitalize on past investments under SERDP or other research programs and are designed to transition technologies out of the lab and into the field. And especially important in all ESTCP demonstrations is the ultimate transition to implementation and regulatory acceptance. Advances in science and technology provide the DoD with the tools needed to effectively manage and restore its assets to protect the troops, families, the public, and the environment. SERDP and ESTCP investments improve installation energy resilience, environmental cleanup, UXO remediation, resource conservation, and the sustainment and maintenance of defense assets. SERDP and ESTCP fund, monitor, and actively guide relevant and applied research, development, testing, and evaluation projects for the DoD's top environment and installation energy challenges. Our programs currently fund more than 600 active projects. To maximize research impact, SERDP and ESTCP collaborate with top talent across sectors. In 2023, we funded projects with 77 academic institutions, 91 federal performers, and 52 industry partners. I think it's especially important to point out on this slide that our work funded is cited 10 times more than average publications. Our innovation and technology development inform DoD policy and ultimately improve environmental and energy management. Our webinar series highlights outstanding projects across all our main focus areas. The next webinar, that is an MR-related webinar, is on November 7th, and this will feature use of unmanned electromagnetic systems for advanced geophysical classification of UXO in underwater environments. Registration is open for webinars through the end of this year. As always, you can find additional information about upcoming webinars at this link. All past webinars are archived and can be accessed via this link. And of course, please save the date for the 2024 symposium, which will be held from December 3rd through 6th in Washington, DC. Symposium registration is open and abstracts for poster presentations may be submitted until August 6th. We would like to remind you that you can get a copy of today's presentation via our webinar webpage. We appreciate it if you please take a moment to complete the survey that will pop up on your screen at the end of the webcast. And at this point, I will turn it back over to you, Jennifer. Thank you for joining us, and I hope you all enjoy.
Thank you very much, Allison. Now, my pleasure to introduce today's first speaker, Dr. Aubrey España, with a principal physicist in the acoustics department of the Applied Physics Laboratory at the University of Washington in Seattle. Over the last 15 years, Aubrey has participated in multiple field experiments and has led the data acquisition strategy during those experiments. Her work has evolved to include classification strategies and performance estimation in the context of UXO remediation and underwater mine countermeasure operations. And it continues to focus on utilizing physics to understand and predict the observed scattering from underwater objects. Aubrey received bachelor's and doctoral degrees in physics from Washington State University. Aubrey, please proceed.
Great, thank you, Jennifer, and good morning, everybody, and good afternoon to those on the East Coast. I would like to just take a moment to thank everybody for taking time to log in and listen to this webinar. So let me start off with a outline of my presentation. So I'm going to start off with a problem statement to give us context for what we're working on. I'm then going to introduce two complementary projects and take you through the high-level objectives and approaches for those, and then talk about the technology that we're really focusing our efforts on. And then we'll get into the meat of the research, which is essentially distilling a complicated physics problem down to a few key elements, figuring out how to incorporate these key elements into a classifier, and then how we can utilize simulation tools to help identify and quantify how important each of these key elements are. And then I will finally end with some potential benefits to the DoD and larger community as a whole. Okay, so the problem statement, I want to tackle this from the context of where we were at for the first project I'm going to talk about, and this was back in about 2019 and 2020. And at that time, systems were being developed and tested at testbed sites, and it became clear of how challenging it was to deploy these underwater UXOs, and thus that would limit the total number of objects that you could put in these testbeds. When you have a small number of contact opportunities, this is going to result in significant error bars on a platform's performance. In addition to this, there's been several workshops over the past decade and a half, and one in particular in 2017 really emphasized the kind of critical effects that target condition have on a system's ability to detect and classify, but then also the grazing angle. And when I say grazing angle, that's essentially how your platform is going to be in sonifying this object. Furthermore, previous work has demonstrated that if you build a solution that assumes that you know all of the clutter items very well, when you move into an environment and are faced with something you've never seen before, you cannot be expected to perform well. So essentially this robustness across environments and clutter was kind of missing. So with that in mind, the high level objectives of these two projects that I'm going to talk about. The first one is MR 201443, and it set out to improve the detection, both real-time and post-mission analysis for UXO identification systems that are incorporating sonar. And then the second project was a seed effort that kicked off last year, and this is number 3978, whose goal was to arrive at a very well-characterized set of surrogate inert UXO, and then ultimately work towards validating, using validated modeling techniques to try to analyze how your system would perform as a function of variation in these UXO characteristics. So both of these, those were very high level objectives. Both of these projects have several tasks and kind of secondary research goals associated with them. For the focus of this webinar, I want to give you kind of this high level view of how these kind of complement each other. So essentially the 1443 is going to take a macroscopic view of the key physics associated with the target, and is going to try to distill this complicated problem down to just a few key elements and try to come up with a way to incorporate these into a classification approach. On the flip side, project number 3978 is going to actually drill down more microscopically. It's going to really dig into the UXO characteristics themselves and try to learn or make kind of quantitative assessments on how these are going to affect classification. It's important to have some context for what we're working on here. So both of these projects are aimed at the multi-sensor tow body system that was developed by the Applied Physics Laboratory. And so this is the MUST system. And again, both of these projects are aimed at transitioning knowledge, tools, simulated data sets to aid in this system. Just high level view, it's a McCartney Focus 3 towfish, and it has a couple of edge tech sensors on it. One is the 2205 dual frequency 5-scan, and the other is the buried object scanning sonar, the EBOS. So there's a lot of information online in final reports and past webinars, but I still wanted to take just a little bit of time to show you the example data products that come out of the MUST system. So the MUST system collects 3D volumetric data. Dr. Tim Marston has put a lot of work into developing EBOS toolkits that give us a lot of flexibility in how we choose to view this data. For the purposes of these projects, I am focused on looking at two-dimensional maximum intensity projection, so MIPS, of these data, but really I'm going to focus my effort on the acoustic color domain. And so this is an angle frequency representation of the data, so it really gets at those structural acoustic responses from these objects. So as I mentioned, this is a very complicated problem. So when you start to say, okay, what are the key pieces of physics that we need to be thinking about and try to utilize? I wanted to set the stage for all the different categories that we're faced with, right? We have variation in the UXO type. Within each class, you have variation in the features of the UXO. They can have different nose caps, they can have fins or no fins. The level of corrosion that they've experienced will affect all this. The presence of clutter can affect things. That could be man-made objects like crab traps and anchors and scuba tanks, or it could be more natural clutter objects like boulders or coral heads. And then finally, jumping into the environment side of things. What type of sediment? What's the bottom type that you're in? Burial depth. Are you close to these clutter items, or are the UXO deployed very closely in a pile or of some sort? So all of these are going to make this problem very complicated. Now, if we illustrate this with data. So we look at, what I've done here is gone back through some old data sets from the MUST system when it was deployed at the test bed at Swim Bay, which is operated by Pacific Northwest National Lab. This particular data comes from 2020 and 2021, so 2 consecutive years. And I'm showing 3 different 155 millimeter howitzers. Each of these howitzers is different. So one has a missing end cap, one has a missing nose, one of them has a buckle and a lifting plug in it. So they each have slight variations. Furthermore, I'm showing you data that spans different burial states. So if you focus on the third column of the third row of data, which is the acoustic color, and you transition from the left side of the screen to the right, you're moving from a crowd scenario to a situation where your nose is slightly buried, to a situation where you're half buried, and then finally deep buried. And so this is just giving you a sense of the level of variation that you can see in actual data for the same class of objects. So how did we set out to simplify this problem given all the factors that feed into this? So we took it from the target side, and that is because our group at the Applied Physics Laboratory, we really know the target physics. So that's what we do best, and so we attacked that side of the problem. Part 1 of this webinar is going to take you through these 2 projects that are really focusing on key ways to deal with the target side of the problem. So how does sound interact with an elastic object? So that's the picture on the left side. Part 2 of this webinar, Dr. Kargl is going to up things a little bit. He's going to say, I'm going to focus on how the sound interacts with these objects within an actual environment, so a simple environment. And you'll see some of these diagrams on the right side that are similar in his talk in part 2 of the webinar. Okay, so when I set out to think about how do we simplify this problem, one of the dominant characteristics of these UXO is that most of them have a cylindrical body. Yes, they might have different nose caps and fins and whatnot, but ultimately their body, the shell of them, is cylindrical in nature. And so the good thing that helps us is that there's been several decades of research into understanding how sound interacts with cylindrical objects. And so I have an image on the right, and I'm not going to go into the details of all the angles associated with all this. It was simply to illustrate that if you are able to insonify a cylindrical object, there are certain angles and frequencies for which the sound will couple on and will actually travel down it in kind of a surface-guided wave. And it can actually produce significant enhancements to the scattering. Now, I said that we've kind of distilled this complicated problem down to simple things, but I still show an equation to say there's still some intense mathematics involved in doing even this kind of simple take on these problems, on these scattering problems. And so you have to, for the type of resonance that you want to look at and predict, you need to be able to derive the phase velocity of that particular resonance. And so that phase velocity is going to depend on shell thickness and the velocities of the actual shell material. So whether it's how fast the sound is traveling through the steel material itself or the aluminum material or whatnot. So once you're able to derive those phase velocities, you can actually use that information to derive a set of coupling curves. So these coupling curves are going to predict where the sound can couple into very specific resonance types in this frequency angle space. And so on the right here, I show an acoustic color template for one of the objects that we've modeled and a series of these coupling curves on there. And I will show kind of a blown up view of this in a couple slides. And so with the help of Dr. Lane Owsley, what he was able to do was take these coupling curves that I'd been able to derive and build kind of these detectors. So essentially these masks based on these coupling curves. So the baseline detector was just a binary mask, and it would just integrate energy in a binary sense, shown in that left figure. He has since created an updated detector that takes more of a continuous measure of degree of fit to the predicted resonance location. And this is helpful because, again, we are deriving all of this just based on a simple cylindrical shell, right? These things actually have tapered noses, they've got fins and whatnot. So we need to account for the fact that there are basically error bars in what we're doing. So here is a blown up view of what we've been able to do with these detectors, so that the three different types of detectors we've developed. So if we look at that same acoustic color plot we saw about 2 slides back, and I look at just half of that so that we can hopefully see those curves a little bit better. We have focused on 3 wave types, so 3 resonance types. Those are shear modes, compressional modes, and then antisymmetric land waves. And I'm not, for the purposes of this, I'm not going into the details of what all of that means. But if you're wanting more information from the physics side, then I encourage you to reach out to me offline, and we can dig into that a bit more. So those 3 wave types are represented by the red curves on that plot. And then we also have some black curves, which if you see, these are the black curves that sweep down in these arcs, if you can make out my mouse. So those are not necessarily a resonance, it is actually a matching condition. And so essentially, if you think about the sound that's coming, the vector of the ray that's going to be incident on this object, and you project that, you look at the axial projection of that, when that projection is an integer number of half wavelengths, then you get a really strong enhancement to these resonances. So what that means pictorially is that at the intersection points of these red curves with the black curves, we should see some peaks. Because the key point here is that these red curves, they're telling us where sound can couple into these wave types. Doesn't necessarily mean you're going to see an enhancement. It's the addition of these black curves helps you point out where you should actually see the enhancement. Okay, so we've made it through building up these detectors and applying them to simple models, and we're at the stage of now trying to apply this to actual data. But in order to do that, we had to convince ourselves, right? We had to address the fact that with the models, you know everything, right? There are no unknowns. We know the shell thickness, we know the material type, we know the exact orientation of what we're dealing with. When you go out to a live demonstration, you know, you don't have any of that information. And so where is the utility in something like this if you have none of that information? And so we were able to prove that we could sweep over a series, so treat these parameters of shell thickness and the different orientations and sweep through parameters and do so quick enough that you actually, it's realistically, you could apply it in kind of a post-processing sense. So you could take data that you have acquired at a live site and in the post-processing phase, sweep through a bunch of unknowns, and you still get a peak where you finally have hit at that true shell thickness and true kind of broadside orientation of this. And so this was kind of a win for us in that we could now envision how this could be applied to real data when you know no ground truth whatsoever. Okay, so that kind of gave you sort of the macroscopic physics, trying to get down to some simple parameters and how we're going to utilize that physics to actually give us another piece of information in the classification problem. Now I'm going to flip over to the more microscopic view. So now, instead of thinking about just cylinders and modes of cylinders, we're going to say, look, let's build up some high fidelity target models and really see if we can characterize these objects really well. And then start to figure out what pieces of these munitions are important and the implications this has in a wider kind of UXO remediation operation. So there were 9 UXO that were loaned to APL from PNNL. They fell within 5 classes. There was actually a 6th class, the 40 millimeter shells, but we just focused our effort on the larger objects. So we spanned from a 60 millimeters up to 155 howitzers. Within each of these classes, there were a number of different variations. So there were multiple types of these munitions. They were in different levels of corrosion. Some had holes in the side, some had noses, some had fins. So there was a wide variety. So within each class, we would create at least up to 6 variations of models for this. So one was just the body, one is the body with a nose cone. You can kind of read that list of different variations. The full 3D versions of these were provided to Dr. Ahmad Abawi in support of his project 1275. Okay, so step one, you got to characterize these things. And so we looked into a number of different characterization techniques. And you know, the first off, you're in the lab with calipers and whatnot, just measuring things. We had an NDT thickness gauge to try to tease out kind of material properties, but also shell thicknesses. And then what's nice is University of Washington has an X-ray computer tomography CT scan facility. And so we were able to send some of these big items that are sealed up and you can't, you know, they're too rusted, you can't get a view inside, and kind of tested out the capabilities of that facility. And you can see that was able to get us an inside look of what the internals of this thing looks like. And then finally, literature research. I mean, just lots of literature, looking through old military documents to understand even down to like the manufacturing procedures, which would help inform what type of material was in use or available at the time. So really digging into these different characterization techniques. Once you have all of that, you can now piece it all together and build up these kind of high fidelity CAD models. So on the left, I show an example of a simple object, which is just a howitzer with an open end. It's all one material. And then we had a lot of challenging objects. So for example, the 105 millimeter M60, that's the one that has internal components to it. So burster well, a fuse cup. There were different nose types that we had, pointy nose. The eye bolt lifting plug nose was challenging. But then the 105 heat, that was another one that was challenging, the fins in particular, right? Dealing with the fins was a challenging piece to that. So the procedure that follows once you have these high fidelity CAD models is you then import these into a commercial finite element software, CONSOL multiphysics. And this was probably the one step that we maybe were the most naive on, in that the more, like the higher fidelity that your CAD model is, the tougher it is, like when you import it in and start trying to mesh things. All these fine details are very challenging. And so there was a lot of learning that had to happen there in dealing with these really fine features. And so that was a big kind of a new step that we took on in this project. Once you succeed in meshing it, you run mesh convergence tests to convince yourself that you've meshed it properly and your acoustic scattering solution is converging. And then finally, the last 2 steps are really the computational burden is building up the bistatic scattering amplitudes, which are computed with our hybrid 2D, 3D FE propagation model. And then these amplitudes are converted to lookup tables for use in the TIR model, the target and environment response model. So these last 2 bullets are going to be covered in part 2 of this webinar by Dr. Kargl. So I just want to show you a quick example of results for a 105 millimeter M60 shell. And I show 3 different objects that I'm going to show you here. So these are all 105s, but with slight variations. On the next screen, here I show the mesh for these 3. So you can now see the differences. Number 1 has the pointy end and all the internals, the burster well and the fuse cup. Number 2, it has no internals in it and is an evacuated cavity. Number 3, we've now put a flat end cap on it. So here's the results of just staring at the acoustic scattering from this. And so you can see that what was interesting, probably intuitive to us from a scattering perspective, is that the filler really makes a huge difference, and more so than just the end cap type, and even whether or not there's a burster well or not. If this cavity has been flooded with water, it looks quite a bit different than if that cavity, if that munition is still intact and is just an air-filled cavity. Okay, so now we're at the stage of where we're starting to try to quantify the effects of all these different target fidelity levels. And so the procedure that we follow, we've built up the CAD models and FE models, we've generated the simulated data, and we have different variations. So kind of these defect models where we've got missing nose caps, missing tails, different types of noses and such. And so we're at the stage of trying to process this simulated data with the identical MUST processing chain to create identical data products that look as though they were collected by the MUST system. And so in the next coming months, I would encourage you to check back and look for a final report that is going to be covering these last two bullets, right? Which is really trying to get to the quantifying from a performance standpoint, and not simply talking about acoustic responses. So in conclusion, I illustrated very briefly two projects that took kind of two different approaches, but were complementary. We went through 1443, which is taking a macroscopic view of those physics and drawing in on kind of the key pieces and distilling it down to just these coupling curves, and how we envision applying this to being able to use this with MUST data. The second project was the SEED effort, 3978, which really then took a microscopic view of the actual UXO characteristics. And we've put in the hard work of characterizing, building up the CAD models, running the FE models, and are now at the stage of being able to use the simulation tools, specifically TIER, in order to start to try to quantify the importance of these from a performance perspective. And so with that, I conclude with the benefits to DoD. And so for system and algorithm developers, these simulated data sets can help you in the development or testing of detection and classification platforms, maybe analyzing different ConOps, different algorithms. For model developers, these CAD models can be used in other simulation tools. The simulated data that we've created could be useful for validating new models. For testbed developers, the UXO inventories historically were not necessarily consistent across the testbeds. And so we may be able to make recommendations as to what would be the best representative set of these inert surrogate UXOs. And then for regulators, having a consistent set of well-characterized UXO at all testbed sites is going to open the door for assessment between different UXO remediation systems. I have some additional resources, and then again, I'm happy to now open it up for questions.
Wonderful. Thank you so much for the excellent talk. I'd like to remind the audience participants right now that you can type your questions into the Q&A box on the Zoom screen. So please type in your questions, and we already have a couple that Aubrey will answer now. You mentioned using this approach in post-processing quickly, but do you think that the elastic axisymmetric object detector is something that could ever be used real time?
That's a good question. So I think in order to get to real time, you would need to cut down the number of parameters, unknown parameters that you're searching over. And so if you had a way of a separate tool that could estimate orientation, right? Or, had a simple way of saying, hey, I think I just flew over something and this kind of looks like a broadside response, right? That would help you lock in one parameter. And then searching over one parameter, that reduces the parameter space that you have to search over. So doing that search over different shell thicknesses is much easier than having to do a search over two parameters. So that would be, I think, what it would take to get to kind of a live, real-time live application of this.
Okay, that makes sense. Thank you. And one physical characteristic that provides the most discriminatory value to a classifier, what might that be?
So I can answer that maybe from a kind of target scattering perspective, but I don't necessarily have the performance curves to back it up yet. If I'm thinking about the elastic axisymmetric detector, the number of arcs that you see is largely dependent on the diameter of the object. And so really the diameter plays a huge role. And if I'm thinking about within a particular class, so if you're trying to discriminate an M60 from a heat or something like that, like you're within some class of objects that has the same diameter, I think the filler is going to make a big difference. Yeah, that's what we've observed from just target physics side.
Okay, great. Next, do you know the swath width of data that the instruments can cover and the line spacing requirement for surveying them? I think this might apply a little bit more to the MUST system. Just checking if you have that.
The swath width. I don't have this information off the top of my head, and I know it's readily available. So I'm happy to just quickly find that and share that offline. Okay. And it could be Steve may recall off the top of his head, but again, I think I'd have to answer that offline.
Okay, that works. You mentioned that some of the CAD models, for example, could be useful to other researchers. So will the CAD models and the FE algorithms, the finite element algorithms, be made available publicly, and how?
Okay, that's a great question. I am happy to work with the program office to make that happen, right? Sharing the CAD models, that's an easy thing to do. And I think that we would just put in a request, right? You know, you would I would recommend emailing me. And then I think that we would need to go through this kind of once, you know, using somebody as a guinea pig, right? To find out where the potential road stops are. For the FE algorithms, meaning so I use COMSOL, I build up a COMSOL mesh and file for it. So an MPH file if you're used to working with finite element software. But the actual running of calculating the acoustic scattering, that's going to be covered in the part 2 of this webinar, where Steve is geared at actually taking his research models and turning them into a tool that can be shared with the community.
Okay, that sounds great. Next, many munitions do have the characteristics that are not symmetric. You mentioned that, the fins or the lifting plugs, or they might have corrosion. So can you just summarize for us how the axisymmetric object detector could still be useful in these situations?
Right. Okay. Yeah, that's a good question. So what I've observed in the acoustic color domain, kind of that structural domain, is that things like lifting plugs and fins don't manifest in huge differences in that particular domain. Now, if you're looking at data in a different domain, where it's the image domain, you get glimpses off of these things, and you can definitely see differences. But if you're approaching this from kind of I'm trying to identify specifically what object this is, those types of things make less of a difference in that kind of larger structural acoustics response. And therefore, that's where I think that this tool can still do well, even despite the fact that it doesn't have built into it some way to deal with these, fins and noses and such. There may have been a second part to that question that I'm blanking on. So if I didn't quite answer it, you could repeat the question again.
Nope, I think that answers it. Thank you very much.
Okay.
I think we have just one more question left for you. Are there differences in construction between the practice munitions used and then the live munitions that would have the potential to affect your results? And I think by practice munitions, they mean, test bed objects.
Yeah, that's, I think that you hit the nail of the problem. That is like the research question moving forward, frankly, is like, how is all of this going to compare to what is actually going to happen out live, right? Because we're building all of these things off of inert objects, and we had a couple of fabricated objects in there so what's the implication of having these classification tools and simulated data and models that are built off of intact inert shells, and how does that compare to what's actually at the live site? Like that is definitely the question, like hot topic in my mind, right? And I don't have an answer to that. But I think that we have the capabilities and the expertise to be able to really head down a route where we could answer that question, right, with more effort.
Okay, great. Thank you very much, Aubrey, for answering these questions. And then we'll have Aubrey come back at the end of the webinar to answer a few more. And now it's my pleasure to introduce our next presenter, Dr. Stephen Kargl, who is a senior principal research physicist with the Applied Physics Laboratory at the University of Washington in Seattle. Steve's current areas of research include the scattering of sound from objects and wave propagation within marine environments. He has served as principal investigator on several SERDP and Office of Naval Research grants and contracts, which address detection and classification of underwater munitions near a water sediment boundary. 2 of the SERDP projects received the Project of the Year designations in 2013 and 2019. Steve received bachelor's degrees in physics and mathematics from the University of Dayton and master's and doctoral degrees in physics from Washington State University. Steve, please proceed.
Thank you for the kind introduction. I'd like to first acknowledge the Munitions Response Program Office for the support over the years. And I'd also like to acknowledge the webinar team for the aid and help they gave me in preparing this talk. This project that I will be talking about started on the 7th of July, 2023. So we're just about a year into the project. The aim of the project is to package up 20 plus years worth of what I call research codes into something that other munitions response practitioners could use without having to ping me for aid. The flow chart at the bottom, Aubrey covered the first part. Here's a UXO on the left. She has a SolidWorks CAD drawing for that UXO. And my contribution and what this presentation is going to focus on is how do you generate stave level? That's how do you generate sonar signals that can then be processed to give you some information about the original target. So for a general overview, the TIR model, or I'll just refer to it as TIR, is a high fidelity acoustic scattering model. The problem with it is it is a research tool, and it's easy for someone not familiar with the internals to be led down the wrong path if they try to run simulations. I will point out that the TIR model has been used to simulate signals to understand the physics of the scattering from objects. And I've listed 4 previous projects, 1665, 2231, 2505, and 1, 2, 3, 4. These are all projects that were led by APL using our rail system to collect data from test beds where we inserted targets into the field and we manipulated the targets so that we could collect data for both validation purposes and also to train and test classifiers. And the second thing that we have used the tier model for is to assess specification for sonar platforms. And MR 2545, which was led by Dan Brown at Penn State, he designed what he refers to as the sediment volume search sonar. This is a platform that's downward looking with about a 1 meter standoff to the sediment, searching for targets that are buried within a mud type environment. And working with Dan in his phase 1, we ran simulations on could he even see at those standoff differences targets of interest, and the answer was yes, and it helped Dan design his sonar system. In MR 18-5004, that was the initial project for the MUST system, the multi-sensor tow body that was developed by Kevin Williams at the Applied Physics Lab. Simulations performed for that system where one of the questions was how many sources should be placed on a tow body to illuminate an environment. And it turned out that we eliminated the fact that we determined that 2 sources were sufficient. A third source would not provide additional information on the environment. And therefore you save design costs. You don't have to design in a third source and deal with the programming of the system. We've also used TIER as a research tool. A very early version of it was provided to Professor Moazzini at Colorado State University for his 2416 project. And what he used TIER for was to augment data that we had provided to him. He had a very limited set of data, and he would needed additional data to train his match space or his match subspace classifier. And he used it to think about how do you take a classifier instead of doing a retraining step, how can you adaptively update the classifications training? And so he used TIER simulations to augment the data, and he also trained a pure classifier on just simulated data and used it to and he ran that classifier against actual measured data. As I've stated, that this is an in-house tool. It's been developed for 20 plus years on both SERDP and ESTCP projects and ONR projects. The tool, I can run it. I'm not sure other people can. So I'm trying to package it to have a decent user interface. There are a couple of basic assumptions I want to go over real quick just to give people a sense of what the model does. There's a global Cartesian coordinate system that describes a scene. It could be a kilometer patch in the ocean with targets strewn on that patch. For the target scattering, we use a local target center coordinate system where we know where the source and receiver are in space, and based on where our target is, we translate everything into the local target center coordinate system. The acoustic propagation is modeled via ray models. Ray models are extremely fast and are applicable to high frequency acoustics, even though we push this down to sonar systems with a lower frequency of a kilohertz. There is a far field approximation where you're assuming that the distance from the source to the target or from the target to the receiver is large. And by large here, we're talking 10 to 20 wavelengths of the carrier frequency of the sonar system. You almost are always in a far field in that you want to have sufficient standoff distance from any kind of ordinance so you don't actually damage yourself if it goes high order. The TIER model can accommodate a number of source apertures. Omnidirectional, that'd be a spherical source, rectangular apertures, circular apertures, or if you have a actual sonar system and you have made a measurement of what its beam pattern is, the TIER model can accept a table of that measurement. There is an additional approximation in that the dimensions of the sources and receiver are assumed somewhat small. And this allows you to illuminate a large area, and most SAS systems meet that requirement. Aubrey mentioned the fact that you have clutter situations. This would be an object of interest next to just a boat anchor or a scuba tank. And so when objects are close enough together, you can have multiple scattering effects where the sound scattered from an object can interact with nearby clutter. That can complicate your analysis of any kind of sonar signal. So TER includes up to fourth order multiple scattering in its capabilities. The environments that TER can currently handle is free field scattering. That would be no boundaries. It targets just in an infinite ocean, and you're trying to understand what is its elastic response. You then have the half space problem where you have a target sitting proud on the sea floor. You have a partial burial in the half space where the target begins to penetrate the sediment water interface. You have full burial where the sediment is assumed to be infinitely deep, or it's just a very deep layer. You can also have a layered environment where you have a thin layer of, say, mud on top of a basement where a target is actually completely buried within the mud layer, and you have to deal with that situation. And it also allows for a homogeneous waveguide. This is where you can no longer ignore the air-water interface. Your sonar system interacts with that interface. And you can have an inhomogeneous waveguide. The difference between those two waveguides is that an inhomogeneous waveguide has a variation in the sound speed as you go down in depth. The TER model right now assumes that the sediment is either a viscous fluid or it can use what's called the effective density fluid model. The difference between these two models is the viscous fluid has a frequency independent attenuation factor, while the effective density fluid model actually has a frequency dependence to the attenuation. So higher frequency attenuates faster in the sediment. The scattering within an environment can be converted to a superposition of scattering problems. This is done by considering a source and a receiver has reflected through interfaces to give you image sources and image receivers. And so I'm going to step through what that would mean for the half space problem. So for the half space problem, you may have a target sitting on a sediment, and you have a source and a physical source and a physical receiver. That would be your left-hand image. You then have in the next image over, so the second from left, a ray that would be launched from the source. It hits the sea floor, reaches the target, scatters to the receiver. You also have the third panel over where the ray hits the target, the scattered field interacts with the sea floor and then reaches the receiver. And you finally have the last right-hand panel where you have a ray from the source hitting the sea floor, interacting with the target, and then interacting with the sea floor again and propagating to the receiver. So that's a very simple physical model for scattering in the half space. You have the boundary interactions introduce reflection coefficients, and that's where you have to start to think about the target in the environment. How does the environment affect what is the sound field incident on your target? So what we end up doing is reflecting the source and receiver through the interface to image sources and image receivers. And when you see one of these dash lines, whether it's a dash blue line or a dash red line, that indicates that that ray has been modified by that interaction with the sea floor. If you sum up all of the contributions from these individual free field scattering problems, they are equivalent to the original problem where you at the top of the page. So the targets that we currently handle in the TER model, you can handle a point target. That's essentially a target that records the incident signal and just re-emits it. There are spherical targets. These are scientific targets that if you can't understand and model a sphere, which you can write down analytic equations for, then you have issues with whatever you're working on. Finite length cylinders are also an analytic model, and these are all targets that allow you to really assess a sonar system. We have 23 objects. These would be UXOs and other scientific targets that have monostatic scattering tables. That would be the source and receiver or co-located. And these were some of the very first models that we created with the hybrid model that Aubrey talked about, and then I've used with the tier model. And we have 19 objects that have biscattering scattering amplitude tables that Aubrey mentioned. I will point out that we actually have information for 21 objects in that Dr. Ahmad Abawi from Heat Light Sound in San Diego has provided me the scattering from some additional UXOs that he has computed that we can't do here. And so I'm in the preparation of additional scattering amplitude tables. Aubrey showed examples, targets. All of the targets on this page, we have scattering amplitude tables for. That allows us to take one of these objects, place it any place in space, place our source and receiver any place in space, and compute what is the scatter field from that target. It could be on bottom proud, it can be buried in a bottom, it can be penetrating the bottom. We can handle this set of targets that you see, as well as some additional targets. So the progress towards actually packaging the tier up into a tool that other people can use. I am a Unix person, and so all of my tools are Unix utilities. These are command line utilities. They do not have a nice GUI interface. They just assume that you can run it at a command line and it reads a simple input data file. The top one, what I call tier, simulates scattered sonar signals. That's the one that you would use if you were trying to assess a sonar system design, or if you're trying to generate data to augment data set, or if you're trying to understand what is the behavior that you are actually observing in real data. The next tool down, which I call PCB, just does a pulse compression and basebands the signal. That's a step that's in preparation of transforming sonar signals into a data product. The data product could be a SAS image, or it could be an acoustic color plot that Aubrey talked about, or you can use it to generate MIP files. The TDI is a 2D time domain beamformer. It's an imager, it's brute force, and it's just meant for me to be able to image my data so I can see it, but I'm supplying it. Other people may want to use other type of SAS programming techniques on the data that can be generated. The acoustic color, A color, will take sonar signals and generate acoustic color templates. Acoustic color templates typically are what we feed into our classifiers. We use them to train classifiers. We use them to prepare data to test classifiers. The last one that is a utility that may be handy is what I call Vox. It's a 3D volume rendering software, which allows you to do a time domain imaging of a 3D volume. There are a bunch of additional utilities that are supplied that can be used for diagnostic purposes. As I said, these are Unix command line tools. They all read an input file that you specify in the command line. The input files allow you to write in units. So if you have say a sound speed in meters a second, you can write in 1,500 meters a second, or you can write in 15,000 centimeters a second if you want. And you can, it understands and will translate the units. The default is to use System International or MKS units. The tier model currently has 3 different types of output. There's a default binary file output that I use. It's the most compact. for the output file sizes. You can select to have the models put out what's known as an HDF5 file. That is a industry standard consortium for file formats. And then you can also ask for it to just spit out a single signal, and it's an ASCII data file, so you can immediately plot it, and that helps assess whether you're have issues with the input parameters for a simulation. So as I said, the PCB utility consumes the tier model output files, and it produces binary files that the TDI, A-Color, and Vox programs use. Each of these utilities has an online manual, so if you forget something, you can look it up easily with the online manual. And the image here is just the very top part of about a 500-line online manual that says, hey, this is how you use this tool. Each of these utilities also has a help message, and that's what's actually being displayed. The help message is a condensed version of the online manual that's embedded in the tool to, again, jog your memory on how to use the tool. The tier tool currently works on FreeBSD. It's a Unix type system that I use. It also has been run on a Ubuntu Linux system, and it's been run on an Ubuntu Linux system that's running under the Microsoft's Windows subsystem for Linux too. So it can be run on a variety of operating systems. So to give you a feel for the tool, what you're seeing here is the bottom of the MUS. That's the yellow system. And I'm going to put the pointer on the screen. This round thing, hopefully you can see it, that's a spherical source. There's a spherical source on the other side of the MUS system. And then the long black item that you see here is a receiving array. The receiving array has 64 elements, and it is mounted on what is known as the Focus 3 tow body. And the tow body is shown below the sonar system. And you can see the size of this system in relation to the size of just a standard male figure. So, you know, it's roughly 6 feet in dimensions. On the right-hand side, I was given data from Tim Marson from a SQUIM test bed for the inertial navigation unit for a transect through the test bed. So it was transect 63. The two black lines you see in the curve on the right are the locus of points for the sources. I've projected the black lines onto the sediment interface, so you see how the vehicle was towed through the system on the water sediment interface. The red portion of these curves represents 301 pings, and that's about the amount of data that's processed at one time to form images within the MUS system. That red area represents about 19,264 signals that you would have to simulate. So I did a simulation where I put a single object in 3 different locations and 3 different orientations. So I had one object that was right below the MUS track. I had one that was about 5 meters to the port side of the system, and then one at about 12 meters. So that's about the entire range of what the MUS system has for a footprint on the seafloor when it's running at 5 meters above the seafloor. So to generate 19,264 signals for 9 different targets with, well, it's 9 different targets, so it's one target with 9 different orientations. It took about 2 CPU minutes on just a standard desktop computer. The conversion using PCB took about 11 CPU seconds, and then the TDI program, the time domain imager, took about 1.6 CPU minutes to generate the images that you're seeing on the right. And in this simulation, all these targets are buried in a sand sediment similar to what would be at Squim Bay, where they're about 1 inch sediment above each target. So the conclusion at this point is the tool is ready for a preview distribution. The distribution method is via APL web portal. And for access, it would be either through permission from the program office where they ask me to give it to you, or you ping me and say, hey, can I get a version of the code? And then I would clear it with the program office that, yes, you have a need for the access. We'll point out that we just got the distribution method set up and functional. Sean Johnson at ARL Penn State is the first guinea pig, and he and I have been working on making sure that he can get to the data and the tool and how he can use it. So a preview is ready. There are a couple of caveats that I need to mention. First is the table format for the bistatic scattering tables is currently undocumented. So a person would not be able to generate their own table and consume it with tier. I'm working on the documentation, and that will be in there on how do you generate a bistatic scattering table. The comprehensive user manual is still under construction. I'm trying to describe both the physics models and the numerical limitation of those models, and how do you use them all cohesively and do it where a user can use it without having to constantly ask me questions on how do you do this. And the final caveat is the tier tool only simulates target scattering. It does not include reverberation from the environment. That's one of the things that I want to work on with Sean Johnson is how do we get realistic reverberation into models. So the benefits to the DoD, the first benefit is the tier tool can aid in sonar design decisions. We've already done that with both the MUST system and Dan Brown's SVSS system. The tier model can do high fidelity simulations where you can augment either available experimental data, or you can pre-train a classifier before you even go to see if you have some a priori notion that, oh, we have 155 millimeters that we're going after, or we have 105 millimeter targets in this environment due to obviously historic notes on what that range may have been used for. And finally, tier can be used for post-mission analysis. You can address questions like, why didn't my system see a target? Or we saw this target, but the physics doesn't make sense to us. What do we expect and what do we find? Again, if there's any additional questions or you'd like access to the tool, you can ping me, or you can ping the program office and they'll redirect you to me, and then we can coordinate on how you can get your hands on the tool. And with that, I think I'm finished.
Great. Thank you, Steve. To our audience, just a reminder, you can submit questions for Steve using the Q&A box on the Zoom screen. Steve, first question. You mentioned that wave propagation is modeled in the tier model via an acoustic ray model. Are there any limitations or issues that occur as a result of this approximation?
Well, the ray models are typically a high frequency approximation. So you're assuming that the sonar signal is at a sufficient frequency where the wavelength is small. And what this really means for us is we've pushed our tier model down to 1 kilohertz. And most sonar systems do not go to 1 kilohertz. They typically, like the MUST system, its lower frequency is 5 kilohertz. So we've used it where some people would say, oh, your array model should be starting to break down. And we haven't seen issues that would not allow you to simulate and draw conclusions from the simulated results.
Okay, great. You noted that reverberation and other sources of noise are absent from tier simulations, have you considered any methods for including noise into the simulated sonar signals?
Yes, actually I have, and there's three answers to that question. The first answer is about 15 years ago, I modeled the scattering from just a rough surface using first order perturbation theory, which allows you to just get a feel for what is the contribution to reverberation from just small scale roughness on a surface. We've also, we're talking with Sean Johnson pre-pandemic on using his POSSUM model, which allows you to actually include contributions to reverberation from inhomogeneities within a sediment. So when you're looking at a sediment bottom, you have fluctuations in density and other little scatters inside the density. And Sean has a model that may be able to handle that. And the final one is Aubrey and I have been talking about, can we take our simulated data for a given sonar platform and embed our results within backgrounds from actual measured data? So there's three different approaches that we're considering for doing this problem.
Okay, wonderful, thanks. You said that the tier model considers 6 environments. Is there one in particular that's the most challenging, and why?
The most challenging one for the tier model is probably the partial burial. And the difficulty there is has an object is penetrating through an interface, you have to track which ray can reach the target and at what point does that ray no longer have the ability to get to the target. So for example, if a target is buried at 45% deep, then rays that hit the bottom can reach the target. But once you get to 50%, no ray that hits the bottom can reach the target except the one that is a direct refracted ray. And so there's this transition of where you turn rays off. It's still somewhat of an open research questions on how do you do that in a manner that is robust.
Sure, that makes a lot of sense. Thank you. And can you comment on the typical size of a scattering amplitude table?
That depends on if you're using a monostatic scattering amplitude table, meaning the source and receiver are co-located. Those tables range from 45 megabytes to maybe 150 megabytes, depending on how densely populated the table is in both frequency and angle space. If you go to a full bistatic scattering amplitude table, it actually is easier to generate numerous tables for different source locations. And then each one of those tables is only 4 megabytes, but you may have 4,000 tables. So it's a bookkeeping problem. So for a full bistatic scattering amplitude, you may have up to 16 gigabytes for a table.
Okay, thank you, Steve. And now, Aubrey, we'd like to bring you back on the line. We have a few questions that are relevant, I think, to both of you. And so the first question is about what is the smallest munition item that you've been able to analyze? And there's also another specific question about is there the potential to detect items as small as 20 millimeter projectiles? And these are questions from the Navy and the Army Corps of Engineers. So Steve, maybe we can start with you on that question.
Well, there's no limit on what tier can do with regard to the size of munitions if there is a scattering amplitude table available for that target. The techniques that Aubrey uses or Ahmad uses can actually provide that modeling information. Now, the problem with those small targets is you definitely need to be aware of what is the reverberation level, because the target strength of a small object is obviously small, and so you're just going to not be able to pull that target out of the background potentially. So the tier model itself can model it. It's whether or not you can actually see it in the real world.
Okay, understood. Aubrey, what do you have to add?
Yeah, I was just going to add from kind of the system, like MUS system standpoint, right? It's just not, from what my understanding of past deployments, you're not going to be able to get below a 60 millimeter object. If you're looking for things that are smaller than that, you're really going to need to make use of different technologies. So whether that be the SBSS or some of the EMI applications. But in terms of, as Steve mentioned, in terms of the modeling and acoustic responsiveness, there's no limitations as to the simulated data that we can create for those. But it is the environmental reverberation. It just swamps it. You just can't see these tiny things.
Okay, that answers the questions, I think. Thank you both. Next, we'll start again with Steve. Can you please comment on the fidelity of the modeling approaches used?
Sure. For the tier model, Aubrey will provide me with the scattered pressure for a target at a specific range, say 15 meters. And I convert that into a table. I can then run tier and compare against data, which is what many of the original APL UW rail experiments were for, is let's collect data on well-characterized targets in a well-characterized environment. So we do validation against experimental data. But then from the modeling standpoint, once I have a single table generated at a 15 millimeter range, 15 meter range, Aubrey can run a simulation again at, say, 30 meter range. I use that table from 15 meter range and reproduce her result at a 30 meter range. So it allows me to say, is the table sufficient to put a target at a different location? And it is, we have not seen anything that says we can't do it.
Okay. Makes sense. Aubrey, anything to add to that one?
Yeah, I could approach it kind of from the target side in terms of the fidelity level of the models, right? So there's a very interesting kind of research question, kind of trade-off space, right? So I'm operating on kind of a standard desktop station. I'm not using any GPU acceleration or cluster computing of any sort. And so as you include really high fidelity features of these things, you got to sit there and wait for quite a while to compute that bistatic scattering amplitude that Steve needs for tier. Once you've done it and invested that computation time, then Steve can go off and you can use tier to simulate anything. But it has been, some of these objects have been a big computational burden, meaning you've got to let it run for on the order of weeks, right? On a standard desktop station. And so how important are tiny little notches, right? How important is the little gap between the fuse cup within like the M60? So those level of fidelity things, right? If you're thinking about the bandwidth that we're operating in for this system, may not be that important, and we could actually simplify these things and lower our level of fidelity. But for the purposes of the seed, we were trying to tackle it from kind of a high fidelity standpoint and see what we could pull off and kind of where those, where we need to maybe start to readjust and say, all right, I think we can dial back the fidelity level of these slightly. And so, but that would be kind of a interesting trade-off space for, kind of a research question.
Mm-hmm. Sure. Okay. Thank you. We have one last question for our speakers today. Aubrey, we'll start with you. As systems are transitioning from deployments at test beds to actual live site remediation exercises, what role do you expect, what you talked about today, the simulated data, what role do you expect it to play?
That's a good question. So I think I'll comment on two things here, right? Is that Steve already mentioned kind of some of in his benefit slide, right? How you can use these simulation tools and simulated data sets. And so to build off of that, I'm just going to echo what he said. The reverberation is not there, environmental reverberation. And so this may be a big problem as you're moving into live sites, right? We just don't know. And so these simulated data sets, we can use them to supplement and help train our classifiers. But as we get into the live sites, we're going to have to potentially reassess based on how these systems actually perform, right? And so I think that keeping in mind the known approximations and things that are missing from these simulated data sets are going to be really important moving forward. But I think they're going to help get people kind of the best prepared they can be for stepping into those live sites. I think another thing is that they can be useful for teasing out kind of the important things to pay attention to, right? If we find that the internals of these things don't make a big difference, then maybe we're less worried as we move, into kind of the real world that we've kind of modeled these perfect shells and whatnot. But again, I think these are open research questions that may need to be addressed after we see how these systems perform under live scenarios.
Okay, great. Thank you, Aubrey, for those examples. Steve, what role do you expect the tool to play going from deployments at test beds to actual remediation?
But I think one of the immediate benefits, at least of the tier tool, is it can make informed decisions for sonar design. The example with the MUST is we initially were thinking we needed 3 sources on that system, and we did simulations, and that third source was redundant. And so we could eliminate that, which then reduces the cost per system when you're building multiple systems. The other aspect is that when you go to live sites, you may not have any training data at all to begin with. So you need to have some way to train a classifier on a set of targets. So hopefully you have some historic information about that location. Are you looking for 155s? Are you looking at 105s? Are you looking at torpedoes? So whatever that munition might be. So you could run something like tier and do a pre-training, and then you could use something like Professor Azimi's ideas on, you have a trained classifier, but can you adaptively update it? And that's where a tier tool may be beneficial to MR practitioner, someone that's actually out in the field. And there's also the thing that after they've made they've done a survey and they come back and say, we didn't see anything, they can ask the question why, and the tier tool would be able to run simulations saying, oh yeah, we couldn't see it because of X, Y, and Z. So that's where I see where the tier tool can be beneficial to the DoD and particularly the munitions response community.
Got it. Thank you so much, Steve. And at this time, we'd like to thank both of our speakers for the presentations and answering the questions. Our next webinar in this program is on Thursday, August 8th, and that's on DoD-funded research to advance the accuracy and promote the use of passive samplers at PFAS-impacted sites. You can visit the SERDP and ESTCP webinar webpage to register for this and all other webinars through the end of this year. Before we conclude, I just want to remind you both the audio and a copy of the presentation from today will be archived on the webinar webpage in case you want to refer to them at any point in the future. We would appreciate it if you could please take a moment to complete the survey that will pop up on your screen at this time. This concludes today's webinar. Thank you.